The object that passed Earth wasn't slowing down, it was positioning. A cosmic documentary sleep story. Part 1, opening the question. Sometimes science doesn't play along. The numbers start acting up. Trajectories that should bend in one direction veer off the map. Then out of nowhere, some visitor from deep space slides past Earth so precisely that even the most seasoned astronomers sit back, stare at their coffee, and quietly dig through data they thought they'd put to bed. That's where 3IATLAS comes in. It's not a dramatic entrance. Just the usual routine. Light hits a detector, the signal turns into coordinates. Those get plugged into the same orbit software that's nailed thousands of predictions before. The program does its thing, spits out the numbers, and suddenly, across observatories scattered over 2 continents, a new path starts to appear on the screens. At first, nobody makes a fuss. The numbers just drift. Not by much, not loudly, but they drift. Tiny deviations, arcseconds, the kind of minuscule shifts that usually get blamed on the atmosphere, tracking hiccups, or one of the 100 little headaches that come with ground-based observing. That's the first instinct. But when you're following something interstellar, something tearing through the solar system at tens of kilometers a second, and stations thousands of kilometers apart all see the same thing, and even the space telescopes, immune to air and weather, confirm it, you can't just shrug it off anymore. You start thinking, maybe the object itself is pulling a move nobody expected. It doesn't fit any of the neat boxes we've built over centuries of watching things glide through the void. And suddenly, those quiet offices where orbital mechanics folks work don't feel so quiet anymore. It's as if the universe just leaned in and whispered, "Figure this out." Nobody's talking about conspiracies. Nobody's talking aliens joyriding past Earth. What unsettles people is way simpler. The data doesn't fit, not even close. The models, those decades-old recipes for how things should move, don't work. And now the logs are starting to show that this interstellar guest, officially labeled a comet, may have pulled off a maneuver in the inner solar system that comets just don't do. Not by accident, not by luck, and definitely not with the creepy precision that tracking stations across America started seeing in late 2025. The tools that caught this aren't second-rate either. Think radio telescopes in New Mexico that can pick up signals from the far edge of the solar system. Optical observatories in Hawaii and Arizona, packed with tech that wipes out the blur of the atmosphere in real time, reaching sharpness you'd expect only from orbit. Hubble, circling above the haze, snapping pictures in wavelengths we can't even see. And James Webb, parked out at L2, peering deep into the infrared to catch the real story behind cold, dark objects. Every one of these instruments, run by different teams, using different methods, came back with the same answer. 3IATLAS wasn't where it was supposed to be. The way it drifted didn't look random. It didn't look like some messy gas jet or ice chunk breaking off. It felt organized, as if the object made a choice. That's the stuff that keeps astronomers up at night. Not the wild, obvious anomalies that shout for attention. It's the quiet ones, the ones that almost don't register. The measurements that are just off enough to bug you but steady enough to demand an explanation. Data that doesn't scream, "Look at me," but instead just sits there, nagging at the back of your mind, leaving you with more questions than answers. In the end, it always starts the same way. A faint glimmer of light caught by a telescope, stamped into pixels and numbers and orbital charts. But somewhere between sighting and goodbye, something shifted. Now, NASA engineers are running late-night simulations. JPL issues statements that sound official but say nothing you can hold on to. And the story isn't over. Before we go any further, here's what this channel's all about. We make cosmic documentaries built for deep listening. These are stories about space that open up slowly, honoring the science and the mystery, never hurrying to a neat answer. Because let's be honest, the universe almost never gives you one. If you start drifting off while you listen, that's not a mistake. That's exactly how we designed it. The cosmos takes its time, and so do we. If that sounds like your kind of ride, hit subscribe. Want more content that treats space as something to meditate on, not just a spectacle? Tap that like button. Now let's turn down the lights and pick up where we left off with our visitor. 3IATLAS showed up in the catalogs on July 1, 2025. The Asteroid Terrestrial Impact Last Alert System, a web of telescopes stretched across Hawaii and Chile, spotted it heading toward the sun. At first glance, nothing seemed off. It looked like your usual long-period comet, maybe kicked out of the Oort cloud by some cosmic nudge and sent wandering for 1,000,000 years before finally dropping in on our part of the solar system. Stuff like this happens. Space is full of drifters. But then the orbital details started coming in, and that's when things got weird. The path wasn't elliptical. It was hyperbolic, wide open, not tied down to our sun. This was a visitor just passing through. The math pointed to an origin way past Neptune, beyond even the scattered disk, all the way out to interstellar space. This wasn't a comet born in our backyard. This was the third confirmed interstellar object we found, hence 3I for Third Interstellar and Atlas after the survey that discovered it. By the time autumn rolled around, every major observatory with a shot at it was watching. Hubble, James Webb, ground-based scopes from Arizona to the Atacama. NASA's Deep Space Network, those giant radio antennas in California, Spain, and Australia, locked onto its coordinates. This was the big show of the season, an object from another star system, drifting through ours and giving us a rare peek at what matter looks like when it forms around another sun. Early data didn't offer any surprises. If anything, it looked textbook. A faint halo from outgassing, spectral lines pointing to water vapor, carbon dioxide, carbon monoxide. The usual chemical signatures of a comet. As 3IATLAS neared perihelion, its closest swing by the sun, slated for October 30th at about 1.4 AU, it got more active. More gas, more dust. Everything lined up with what you'd expect from an icy wanderer from deep space, warming up under our sun, following the rules of physics. Then it swung past perihelion. Then it drew closer to Earth. And that's when things started getting strange in a way that even the tracking stations couldn't quite pin down. The trouble crept in, slow and quiet, the way most scientific mysteries do. Not a lightning bolt, just a stubborn pattern that wouldn't fit. Our predictions for its path, based on the same gravitational math that steered probes to the far corners of the solar system, started falling out of sync with where we actually saw it. At first, the gaps were tiny. The kind of thing you might chalk up to a bad measurement or a bit of atmospheric noise. Almost. But with something moving at tens of kilometers per second, even small errors add up fast. And when observatories on opposite sides of the world all see the same mismatch, it's not your equipment, it's your assumptions. Those assumptions were pretty basic. After passing the sun, 3IATLAS should have been coasting on a simple ballistic route, its path shaped only by the gravity of the sun, Jupiter, Earth, and the rest. Sure, comets can get nudged a bit by outgassing, but we know how to predict that. It's tied to sunlight and drops off as the comet heads away from the heat. By mid-December, when 3IATLAS was closest to Earth at 1.8 AU, that outgassing should have faded to almost nothing. The trajectory should have smoothed out, but it didn't. NASA's team at the Center for Near-Earth Object Studies, tucked inside the Jet Propulsion Lab in California, spotted it first. Their models predicted 3IATLAS should show up in one spot. Instead, the real thing, double-checked by ground stations and even a few space telescopes, drifted somewhere else. Not by much, but enough to notice. And here's the weird bit. The shift followed a pattern. It wasn't just random noise. It looked like something nudged it, and not by accident, like it got a push in a particular direction. Now, this is the part where most TV specials would jump straight to the wild stuff. Cue the dramatic music, some grainy reenactments, and a few sly hints that aliens might be steering the ship. But that's not how real science plays out. If you're a researcher, that itch of uncertainty stays with you. You remember that big claims need big proof. And big proof means you have to knock out every normal explanation before you even start thinking about the weird ones. So before we get into what 3IATLAS could be up to, let's talk about what comets usually do, and why this one is making people uneasy. Part 2, the expected discovery. People have watched comets for longer than countries have existed. For ages, We stared up at those bright streaks across the sky, wondering if they were omens or messages from the gods, maybe even warnings of big changes ahead. Ancient Chinese astronomers were already jotting down notes about comets way back in 240 BCE, carefully logging every appearance in the emperor's records. In medieval Europe, folks usually panicked when they saw a comet. They'd brace for plagues, wars, or the deaths of important people, anything bad, really. The Great Comet of 1680 actually showed up in broad daylight, and that just sent everyone in Europe into a frenzy of doomsday fears. Then there's Halley's Comet, which swings by every 76 years. It was the first comet to have its orbit worked out and its return predicted, which was huge. Suddenly, comets weren't just supernatural warnings. They were part of the natural world, following rules we could figure out. Newton showed up, brought gravity into the picture, and suddenly comets were just icy, rocky leftovers looping around the sun. The magic was gone. Comets stopped being omens and became science projects. By the 1800s, astronomers had gotten so good at calculating their orbits they could predict returns decades ahead. Fast forward to the 1900s and we're sending spacecraft to visit comets, landing on them, even analyzing what they're made of right there on the spot. The fear turned into curiosity. The mystery turned into math and data. We didn't have all the answers, but we figured we could get them. This shift, though, came with a kind of quiet confidence, maybe too much. We started to believe we knew what comets were, how they acted, and what rules they followed. The thinking went, sure, some details might surprise us, but the basics are nailed down. And honestly, for comets that orbit our sun, the ones born in the same dusty cloud as Earth, that confidence held up. We could track their paths, predict their visits, and explain their weirdness with neat equations. Then along came interstellar comets, and they messed with that sense of certainty. These are objects from other star systems, shaped by conditions we might not even know about, exposed to stuff we can't recreate or fully imagine. They might look and act a lot like the comets we know, but there are differences, sometimes subtle ones, that our best models just don't see coming. By the 21st century, tracking comets wasn't exactly easy, but it was standard practice. A network of automated telescopes scans the sky nonstop, snapping photos hours or days apart, hunting for anything that moves differently than the background stars. When something shifts, software catches it. Then a human checks the alert. After that, the math kicks in. Within hours, or at most, a few days, astronomers know where it came from, where it's going, and when it'll get there. The US runs some of the most advanced tracking systems out there. The Minor Planet Center, NASA-funded and run by the Smithsonian in Cambridge, Massachusetts, serves as the clearinghouse for reports on asteroids, comets, and anything else zipping around out there. Every discovery goes through them. Every orbit gets calculated there. It's the nerve center for planetary defense, the alarm that goes off if anything dangerous heads our way. When Atlas spotted 3IATLAS, the playbook unfolded perfectly. First sightings came from Hawaii. Chile confirmed. The orbit turned out to be hyperbolic, meaning not from around here. Astronomers checked old sky photos to see if anyone had missed it before. Within 2 days, it was officially marked as interstellar. Within a week, observatories all over the globe were pitching in with their own data. All this rapid-fire coordination depends on decades of investment and tech upgrades. The Minor Planet Center's database holds orbits for hundreds of thousands of objects. From giant asteroids to barely their comets, you need a massive telescope to see. Automated software can match a new object to the database in seconds, flagging if it's something we've already seen or something brand new. For interstellar objects, the giveaway is orbital eccentricity, a number that tells you if the orbit is open or closed. If it's less than 1, the object's part of the solar system and keeps coming back. Greater than 1, it's passing through, never to return. That's how we know when something truly alien has dropped by. Figuring out an object's eccentricity isn't something you do in a single night. You really need a series of observations, spaced out over time. One sighting just pins down where the thing is, but you have no clue about its speed or which way it's headed. 2 sightings help, you get a sense of direction, but you're still mostly in the dark about its real path in 3 dimensions. Add a third, and now you're starting to box in its orbit. Once you have 4 or more observations from different nights, you can finally piece together the object's trajectory with decent confidence and actually calculate its eccentricity well enough to tell if you're looking at something bound to the solar system or a true interstellar wanderer. Take 3IATLAS as an example. Atlas in Hawaii first caught it, and its movement lined up with what you'd expect from a long-period comet swinging in from way out beyond Pluto. But when astronomers added more data from other observatories, the numbers shifted. The calculated eccentricity came out to 1.001, just enough over 1 to tip it from a long-lost solar system object to a visitor from another star. That tiny nudge above 1 makes all the difference. These calculations aren't just nitpicking. Small errors in observation can bump that eccentricity up or down. If you're off by just 0.002, you could mislabel the object completely interstellar or local. That's why astronomers double-check with telescopes all around the world, each using their own equipment, to rule out anything weird that might throw off a single measurement. When observatories in Hawaii, Chile, Arizona, and California all came back with the same results, a hyperbolic and therefore interstellar trajectory, the case was pretty much closed. Spotting a new interstellar object sets off a whole chain of events, thanks to procedures put in place after Oumuamua surprised everyone. NASA's Center for Near-Earth Object Studies gets the word out fast to astronomers worldwide. Space agencies are alerted, ESA with its Gaia telescope, JAXA in Japan, since they're pros with comets and asteroids, and anyone else who might have a useful instrument pointed at the sky. Within days, the whole community is working together, scrambling to get as many eyes and instruments on the object as possible. The science goals are big. First, nail down the orbit so precisely you could, in theory, trace it back to the star system it came from. Then, use spectroscopy to figure out what it's made of, what elements, what molecules, and in what proportions. They'll also try to pin down its size, shape, and how fast it's spinning, using brightness variations and, if they're lucky, direct images. If anything weird crops up, strange chemistry or behavior that doesn't fit normal physics, or even the faintest hint of artificial origin, they want to catch it. The idea is to build such a detailed record that, when the next interstellar visitor shows up, astronomers can compare notes and start seeing bigger patterns. Pulling all this off means getting a bunch of big, expensive telescopes to drop what they're doing. Observatories like the Keck twins on Mauna Kea usually book their time months ahead, so convincing them to switch gears isn't trivial. Scientists have to argue, sometimes pretty forcefully, that this new target is worth pushing aside everything else. When you're talking about an object from another star, it's a strong argument, but there's always a scramble, some back and forth, and a lot of juggling schedules and priorities. Space telescopes are even trickier. Hubble and Webb can't just point wherever you want, whenever you want. They have to avoid parts of the sky for technical reasons, solar glare, heat issues, mechanical limits on how fast they can spin around. To get them aimed at an interstellar object, you need to file proposals, make your case, and wait your turn, sometimes weeks in advance, all while the object's speeding away. And the clock is always ticking. These objects move fast and predictions about their path always have some fuzziness. Wait too long and your chance slips away. The thing gets dimmer, farther, and harder to study. Miss that window and you've lost data forever. That's why astronomers often rush in, grabbing any chance to observe, even if conditions aren't ideal. It's better to get something than nothing at all. Comets, especially ones from other star systems, are a mess, literally. They aren't solid rocks but loose clumps of ice and dust, forming way out in the coldest parts of planetary systems where stuff like water, carbon dioxide, and methane freeze solid. When they swing close to a star, the heat makes the ice vaporize straight into gas, skipping the liquid stage. This process creates the familiar coma, a fuzzy cloud wrapped around the core, and the tail, That glowing stream of gas and dust getting pushed away by sunlight and the solar wind. Outgassing doesn't just make a comet look pretty, it actually gives it a push. When gas jets shoot out from the surface, they work like tiny rocket thrusters, nudging the comet this way and that. Astronomers know all about this. They factor it in when they plot a comet's path. The tricky part is that push isn't the same everywhere. It depends on which side of the nucleus faces the sun, how fast the comet spins, and what it's made of inside. To predict these weird, non-gravitational forces, astronomers have to keep an eye on the comet over time, checking how its real path drifts away from what gravity alone would predict, and then tweaking their models to match up. For comets that belong to our solar system, this whole process runs smoothly. We've tracked thousands. We know their patterns. We can pin down their orbits and future visits. Some comets are so familiar that we can say exactly where they'll show up decades from now, factoring in both gravity and outgassing with remarkable detail. But 3IATLAS wasn't a solar system comet. It came from somewhere else entirely. Its ice didn't freeze out of our sun's nebula, but from another, around some distant star under different conditions. Maybe it had a strange water-to-carbon dioxide ratio, or carried odd ices like carbon monoxide or methane. Maybe its core was built differently, its dust and organics arranged in ways we'd never seen. All of that means its outgassing could act nothing like what we're used to. That's the whole point. Interstellar objects are exciting because they're different. They show us how planets and comets might form across the galaxy, not just in our neighborhood. Remember when 1I/Oumuamua zipped through back in 2017? It sped up in a way nobody could quite explain. Some scientists thought it was outgassing, just invisible. Others tossed around wilder ideas, even suggesting it might be artificial. Nobody really settled the debate. When 2I/Borisov showed up in 2019, it was a relief. It looked and acted like a normal comet. Classic coma, bright tail, just what we expected. Astronomers relaxed a bit. So when 3IATLAS first appeared, it seemed like another Borisov. An interstellar comet, yes, but one that followed the rules. Observatories tracked its coma, measured how much gas it was throwing off, and checked its light for chemical fingerprints. Everything lined up. The trajectory models included non-gravitational tweaks for outgassing, just like always. The predictions looked solid, and for a while they were. Through September and October, right through its closest approach to the sun, 3IATLAS stayed on track. The folks at JPL, the Minor Planet Center, and observatories everywhere followed the data and felt good about it. Just another well-documented visitor from the stars. Another piece of the puzzle. Then, after perihelion, as Atlas swung back out and started heading toward Earth, things got weird. It started as a small glitch. Astronomers kept adding new observations, refining the orbit calculations like they always do. Usually this just means tiny tweaks, adjusting decimal points, that sort of thing. But as December 19th and Atlas's close approach drew near, the numbers refused to settle down. The new data didn't tighten the predictions. It broke them. At first, people blamed the usual suspects. Maybe the weather was messing up the readings. Maybe a telescope needed recalibration. But then the Hubble Space Telescope chimed in. Hubble doesn't care about clouds or turbulence, and it saw the same problem as everyone else. Suddenly, tracking teams were emailing back and forth, hopping onto conference calls, swapping data, checking and double-checking every measurement. No matter how they sliced it, the result was the same. 3IATLAS wasn't following the path that gravity and known outgassing said it should. The difference wasn't huge, but it was real, consistent, and impossible to ignore. And then there was the direction of that drift. This wasn't just a random wobble. It wasn't the sort of chaotic meandering you'd expect if outgassing was just misbehaving. The change was pointed. It had a direction. It was as if the object had made a choice, nudged itself from a path that would have kept it farther from Earth to one that brought it closer, altering the encounter in ways you could calculate but not quite explain. People started whispering about positioning. You didn't see the word in any official statements or polished research papers, just in the offhand remarks between scientists who'd spent their lives with orbital mechanics and could spot when something didn't add up. Positioning meant someone, or something, had a plan. It meant control. It meant maybe 3IATLAS wasn't just tumbling through the solar system, but steering itself, for reasons nobody could figure out. That's not the kind of idea you toss out in public. Say it without rock-solid proof and you're finished. So as always, everyone fell back on the usual playbook. Look for the simple answer, check the instruments, poke at the data, consider if something boring and overlooked might be messing with the numbers. But late at night, when the labs were quiet and the noise died down, you could feel the unease settle in. Maybe, just maybe, the universe was about to throw them a curveball they weren't ready for. Part 3. When the data refused to behave. Before sunrise, an observatory settles into this deep, almost eerie calm. You hear the telescope slowly sweeping across the sky, motors humming, domes turning to keep up with targets as the planet spins beneath a sea of stars. Inside, control rooms glow with the light of monitors, each screen covered in data streams. To most people, it's just noise. But for those who know how to read it, it's a map of distant worlds, coordinates, velocities, details from millions of kilometers away. Then came December 2025, and that calm disappeared. Suddenly, observatories all over the United States were buzzing with activity. From Mauna Kea's Keck Observatory in Hawaii to Lowell Observatory out in Arizona, astronomers watched 3IATLAS as it made its closest pass by Earth. Nobody was worried about danger. The thing stayed 1.8 astronomical units out, about 270 million kilometers, so farther away than the sun. No, it was all about the chance. This was the best look we'd get at an interstellar visitor before it vanished into the dark again. But trying to pull off a project like this, it's a logistical nightmare. Telescope time is gold. Every observatory has a long lineup of projects, all hopping for a slot. Getting everyone to focus on one target means tough conversations at the top, arguments over what's most important, and sacrifices for other research. But when something from another star system drops by, it's hard to argue against it. This wasn't just another icy rock. This was a messenger, evidence from places we'll never reach, clues about how planets form in distant systems, and maybe a hint at what else is floating around out there. The observations had to be exact. Astronomers used optical telescopes to snap images through different filters, tracking shifts in color and brightness. Spectrometers broke the light down, showing which molecules hid in the coma. Infrared telescopes checked for heat, picking up dust and ice activity that visible light might miss. Even radio telescopes joined in. Though the object was too small and far for a direct signal, they listened for anything odd, just in case. Every night, these sessions spat out a pile of data, hundreds of megabytes from the big telescopes alone. Raw detector files needed careful processing and calibration. Astronomers had to correct for quirks in the instruments and the atmosphere. And the weird part, the photons hitting those detectors had left 3IATLAS minutes or even hours before. By the time anyone saw the data, the comet was already somewhere else. So tracking it meant constant updates, new predictions, new coordinates, a never-ending loop of observing and recalculating, night after night. Somewhere in this non-stop grind, something odd started to show up. Not in a single chart or a single night's work, but in the hands of the teams doing orbit calculations, the folks who stitched together observations from all over all times. To map out a trajectory as precisely as possible, these teams, like the ones at NASA's Jet Propulsion Lab, used software honed over decades. It included everything: general relativity, the pull of every major body in the solar system, even tiny pushes from sunlight and outgassing. Here, how it worked. You gather every observation, fit an orbit to them, predict where the object will show up next, and compare those predictions to the new data when it rolls in. If the prediction matches the observation, you're good. If it doesn't, you've got a problem. Either the data's off or your model is missing something. For 3IATLAS, through September and October, everything lined up. The comet moved just as gravity said it should, with only small tweaks for outgassing. But as November rolled in and the comet swung past perihelion heading back out, the predictions started to slip. Something was off. At first, the signs were subtle, just a few odd numbers showing up. The predicted positions and the actual ones started drifting apart, but not by much. It was the kind of thing you could blame on measurement quirks or maybe a tweak needed in the outgassing model. But the gap didn't go away. It got bigger. By early December, with 3IATLAS closing in on Earth, the difference was glaring. No one could brush it off as noise anymore. The engineers dove in. They ran all the usual checks. Was the telescope tracking off? Nope. Were the timestamps right? Yep. Coordinate systems, software bugs, anything that could have thrown off the orbit calculations. They looked at everything. It all held up. The data was solid. The software was fine. So the problem wasn't in the tools. It was in the physics, or really in the assumptions they'd made about what forces were acting on 3IATLAS. And that's when the routine turned into a real mystery, all because of those December nights and the pile of new data. Orbital mechanics is usually straightforward. You get an object's position and speed. You factor in gravity from the Sun, plus a nudge from Jupiter, Saturn, maybe Earth, and you can figure out exactly where it'll go. These calculations are so reliable that mission planners can send spacecraft zipping across the solar system and hit their tiny targets every time. But there's a catch. You have to know all the forces at work. For comets, that means adding in the push from outgassing. Gas jets shoot out from the nucleus and act like little thrusters. This effect isn't just theoretical, you can measure it, and once you spot the pattern, you can predict it too. Watch how the comet drifts off its gravity-only path. Fit a model to that drift and you're set. That's because outgassing behaves. Sun heats up the comet, outgassing ramps up. Comet swings away from the Sun, outgassing drops off. The push should follow a rhythm tied to the comet's spin, so you get a repeating pattern as active spots face the Sun. The thrust should point away from the Sun, more or less. But 3IATLAS didn't play by those rules. The weirdness didn't just start after perihelion, it got worse. Instead of calming down as the comet moved away from the Sun, the offset actually grew. And the direction, not away from the Sun, not toward it, but sideways. Perpendicular to the Sun-comet line. It made no sense. Solar heating should have mattered, but the data didn't care. JPL's engineers kept crunching the numbers. They fiddled with the non-gravitational forces in their models, searching for something, anything, that would explain what was happening. Maybe a hidden stash of volatile ice had suddenly vented. Maybe the comet's spin was off-kilter. Maybe there was some weird heat source inside, keeping parts of it active even as it got farther from the Sun. Every idea hit a wall. The models that worked before perihelion just didn't match what happened later. Fix the December data, break the October predictions. It was like 3IATLAS was living by two different sets of rules. And then, right in the middle of all this confusion, the brightness started acting up. Comets usually put on a show as they get closer to the Sun. More ice turns straight into gas, kicking up clouds of dust that catch sunlight and brighten the whole thing. As they move away, that activity slows down and the comet fades. It's a pretty solid pattern. Astronomers can guess how bright a comet will get just by knowing how big it is and what it's made of. But 3IATLAS didn't play along. When astronomers tracked it, using everything from backyard telescopes to the big NASA-funded ATLAS survey that first spotted it, they saw brightness changes that just didn't fit. Sometimes the comet would brighten out of nowhere. Other times it stayed at the same brightness when it should have been fatting, then suddenly dimmed before picking up again. These weren't huge changes, just about half a magnitude, hardly enough for most people to notice. But they were real. And they didn't match what you'd expect from normal solar heating. Some scientists thought maybe the comet was tumbling, with an oddly shaped nucleus reflecting sunlight differently as it spun. That can happen. A lumpy comet turns, and the amount of sunlight it bounces back shifts in a regular rhythm. But with 3IATLAS, the changes didn't follow any clear cycle. No pattern, just random ups and downs. Others figured maybe it was having little outbursts, sudden blasts of gas from under the surface. That's not unheard of. Sometimes a pocket of frozen gases thaws, vents quickly, and the comet briefly flares in brightness. Usually, though, you see the signs, jets shooting out weird shapes in the glowing coma, but nobody spotted any of that. The coma looked smooth, pretty much the same all around. No obvious jets, no lopsided features that would point to big outgassing events. And that's weird. If outgassing was strong enough to nudge the comet off course, measurable, not just a tiny wobble, there should have been clear jets. Gas and dust should be blasting out, showing up as streaks or fans in the images. That's how astronomers usually figure out which parts of a comet are active. But 3IATLAS showed a calm, even coma, hinting at only gentle, even outgassing, not the kind of focused jets that could shove the comet around. So now there's this puzzle. Dynamically, something was pushing the comet, but photometrically, there was barely a hint of anything strong enough to do the job. Maybe the outgassing was somehow invisible, happening at wavelengths we weren't watching, or maybe something else entirely was messing with its path. We actually know a fair bit about how cometary outgassing works, at least for comets in our solar system. When a comet gets warm enough, say above 200 Kelvin for water ice, the ice turns to gas and escapes. At the distance 3IATLAS was in December, about 1.5 to 2 times Earth's distance from the Sun, it should have been in that temperature zone, depending on how dark or shiny its surface was. So water ice could have been doing its usual thing. But when water sublimates, it doesn't hide. The gas glows at certain ultraviolet wavelengths, and telescopes can pick up those signals. The gas also lifts dust, building the comet's coma and tail. If there are jets, you can spot them, bright streaks, fans, or lopsided comas, all depending on where the sun hits and how the nucleus spins. 3IATLAS gave mixed signals. Ultraviolet observations showed hydroxyl emissions, proof that sunlight was breaking apart water molecules. But the emission wasn't all that strong, so the outgassing wasn't particularly intense. The coma itself, in visible light, looked smooth and round, not marked by bright jets or streaks that would point to active directional blasts. Some astronomers wondered if the gas was sneaking out through subsurface channels, vents that never quite broke through the surface to make visible jets. The idea is, gas builds up under the crust and seeps out through cracks or pores, giving the comet a push without leaving obvious marks. It's possible. A few comets in our solar system seem to do this. But it's rare, and it needs a very particular internal structure, not something you can count on for every comet. Maybe the active region sat on the night side of the nucleus, the half facing away from the sun. Sounds odd, right? Sunlight drives sublimation after all, but thanks to thermal inertia, the hottest spots on a spinning object can actually lag behind the area getting direct sunlight. If the nucleus was a slow rotator, and if it held onto heat well, outgassing might actually peak hours after local noon, maybe even once those regions had already spun into shadow. That could explain why we didn't see any jets. They were blasting away on the side we couldn't see. But this idea had its own problems. Even if outgassing happened on the night side, the gas and dust should eventually drift into sunlight and start scattering photons toward Earth. Plus, the change in trajectory was bigger than you'd expect from the kind of slow, delayed outgassing this scenario would cause. The brightness changes made things even stranger. Teams at the University of Arizona's Catalina Sky Survey and Lowell Observatory kept an eye on 3IATLAS, tracking how its apparent magnitude shifted over days and weeks. Sometimes it would brighten by 0.3 to 0.5 magnitudes, hold steady for a few days, then fade again. This up and down cycle kept happening through November and December, even as 3IATLAS moved farther from the sun, when you'd expect activity to drop off. Comet brightness changes can happen for lots of reasons. Sometimes it's just the rotation. If the nucleus is shaped like a potato, it shows off different sides as it tumbles. Outbursts can suddenly unleash gas and dust, making the comet flare up. The dust in the coma can change how it scatters light as particles age or break up. Or maybe something blocks the nucleus for a bit, dust or gas drifting in front, causing a dip. The weird thing was, none of these explanations really fit what we saw. If it was just rotation, you'd see a regular pattern. Outbursts are usually quick. Changes in scattering happen slowly. But 3IATLAS kept showing these irregular brightness jumps, No clear rhythm, longer lasting than typical outbursts, but sharper than you'd expect from slow dust changes. Then there was the timing. The biggest brightness swings happened right when 3I/ATLAS was closest to Earth in mid-December, the same window when its weird trajectory shift stood out most. That's suspicious. If outgassing was behind the trajectory change, and outgassing also adds dust and brightness to the coma, then having both effects peak together makes sense. But we didn't see jets, the coma looked smooth, and the pattern of changes just didn't match what you'd expect from simple outgassing. So some researchers started thinking outside the box. Maybe 3I/ATLAS had a lot of dark, non-reflective dust, stuff that soaks up sunlight instead of bouncing it back. That could hide obvious brightening, even when things got active. Or maybe the nucleus was made of material that sublimated straight into gas, without crumbling into dust. That would give you a gas thrust, but with no visible dust coma, a rare, but not unheard of behavior in comets. Another idea. Maybe the object wasn't spinning neatly on one axis, but tumbling chaotically. If so, the sun's heat would hit different areas in an unpredictable way, causing outgassing to sputter on and off, always pushing in new directions. Over time, all those random little thrusts could add up, giving the appearance of a steady acceleration, even though it was just chaos under the surface. That theory had a certain appeal, irregular behavior, but nothing truly bizarre. We've seen tumbling in asteroids and even some comets. The catch is, it's hard to prove. You need a lot of photometric data, taken frequently over long stretches, to pin down the rotation state from light curves. With 3I/ATLAS, observations were common but not continuous. Bad weather, telescope schedules, and the comet's position in the sky left gaps. That means subtle patterns could easily slip through the cracks or get misread entirely. By mid-December, as 3I/ATLAS swung past Earth and started its journey back toward interstellar space, another oddity showed up. The object wasn't slowing down the way it should have. Everything slows down as it climbs out of the sun's gravity well. Throw a ball up, it falls back. Send a comet out of the solar system, it loses speed as it goes. That deceleration depends only on the sun's mass and how far the object is. It's basic, rock-solid orbital mechanics. 3I/ATLAS was slowing down, but just barely less than expected. The gap was tiny, less than a meter per second in speed, but it showed up again and again, every time someone checked. Something was giving it a faint, steady push, nudging it along and fighting against gravity's gradual slowdown. This was the heart of the whole puzzle, not because it screamed alien technology or anything wild, but because it just refused to fit neatly into what we thought should happen. A change of a meter per second. On human scales, that's nothing. Blink and you'd miss it. But stretch that out over months, years, and suddenly you're talking about a real difference. By the time 3I/ATLAS leaves the solar system, that little bit of extra speed could mean it ends up reaching some far-off place years ahead of where a simple, gravity-driven path would take it. If you were building an interstellar probe and your fuel was precious, you wouldn't waste it all at once in flashy bursts. You'd ration it using slow, gentle thrusts, just enough to keep nudging your course again and again, letting those tiny changes pile up over huge distances and years. You tweak your path quietly, carefully, always watching the fuel gauge, always staying just under the radar. Of course, that's just one idea. The real answer might be much more mundane. Maybe there's a bit of gas venting from the object, just enough to give it a push. Maybe there's dust dragging on it in some way we haven't quite figured out. Or maybe we're just not measuring the speed as accurately as we think, especially when the object is so faint and far away. Science means chasing down every ordinary explanation before you let yourself believe in something extraordinary. And right now, the regular explanations for 3I/ATLAS, the boring ones, aren't quite used up yet. But honestly, it's the wild ideas that keep astronomers awake. They're what make people pitch new theories, ask for more telescope time, or dream up better instruments. Because if the wild idea is right, if one day we really catch something from another star system steering itself through our solar neighborhood, the shockwaves wouldn't stop at astronomy. It would shake up everything we think about ourselves. It would mean we're not the only game in town. It would mean intelligence popped up somewhere else, got good enough at science and engineering to travel between stars, and decided to swing by our sun. Suddenly you're left wondering, why? Are we being watched, judged, or just ignored like background noise? Is this object supposed to talk to us, or is it just gathering data and moving on? Honestly, even writing those questions out loud feels a little ridiculous, like I'm pitching a sci-fi movie instead of talking science. But that's the thing, they're not ridiculous. They're just the logical next steps if you let yourself wonder whether everything out there really is natural. Thanks to 3IATLAS, those questions are a lot harder to wave away. And then there's the timing. People noticed that the weirdest changes in its path happened right after it cruised past Earth in December, right where our gravity should have had the biggest say. If you wanted to change direction using a planet's gravity, that's exactly when you do it, right at closest approach. You make small tweaks while you had the most leverage, letting Earth's mass do most of the work and saving your own energy. That's not just science fiction either. This is how we send our own spacecraft into the outer solar system. Voyager used Jupiter and Saturn for speed boosts, slingshotting around them. Cassini ping-ponged past Venus, Earth, and Jupiter to get to Saturn, a careful dance of flybys and timing. It's smart, it's efficient, and you have to get the details just right or you miss your shot. 3IATLAS was never supposed to be anything special, just a chunk of ice, minding its own business, drifting along like any other comet. But then its trajectory started pulling tricks no one expected. Some people thought it almost looked like the thing was steering itself, like it was pulling off a gravity assist on purpose. It wasn't that they believed it was intelligent, just that the timing and angles felt a little too neat, almost suspiciously so. Plenty of skeptics jumped in, of course. People are wired to see patterns everywhere. Faces in clouds, secret messages in static, you name it. Toss us a weird data set and we'll spin a story out of it, even if there's nothing there. Maybe the comet's path shifted because of outgassing we missed, or maybe we messed up the measurements, or maybe there's just some natural process we still don't get. Either way, nobody wanted to go out on a limb and claim this thing was maneuvering, not without rock-solid proof. That's not the kind of mistake you want to make in front of your peers. Still, the numbers didn't lie. 3IATLAS was different. Maybe it was something big, new physics, something nobody had seen before. Or maybe it was just another gap in what we know about comets from other star systems. By late December, as the comet slipped out of sight and the chance to study it faded, one thing stood out. It hadn't behaved the way everyone expected. It broke the rules just enough to keep people guessing. And now, the scientists, just as human as anyone else, were left digging for answers, uncomfortable and intrigued, trying to figure out what they'd actually seen. Part 4, Scientific Silence and Human Limits. There's a special kind of pressure that builds up in science when the data hints at something odd, but doesn't really prove anything. It's not the excitement of a breakthrough, or the calm satisfaction you get when a mystery finally clicks into place. It's slower, heavier, a pileup of questions you can't answer yet. You know you're staring at something important, but you just don't have the tools or enough time to figure out what it means. You see it in the way people act at journal clubs, those meetings where researchers share new findings. The whole conversation feels tentative. People hedge their bets. It appears that, or the data suggests, or maybe one way to look at it is, the usual confidence you hear from scientists fades, replaced by caution. Someone floats a theory and right away, someone else pokes holes in it. Explanations get tossed around and shot down. The discussion just circles, never landing anywhere solid. Everyone senses they're reaching for answers they can't quite touch. Step outside those formal settings and the tone changes again. In private, scientists admit they're confused. They say things they'd never write down. They ask questions that blur the line between science and philosophy. What if our models are wrong in ways we haven't even dreamed up? What if our labels, asteroid, comet, planet, just don't fit what's actually out there? What if we've just been incredibly lucky not to run into something truly bizarre until now, and that luck about to run out? These aren't just idle musings. This is how astronomers keep their minds open when the universe throws curveballs. It's a way to get ready for the kind of surprises that force science to change. That's always been the story in astronomy. Weird observations push us to rewrite the rules. Uranus's weird orbit led to Neptune. Mercury didn't move the way Newton said it should, so we got Einstein's relativity. Nobody expected the cosmic microwave background. When it showed up, it changed everything. Each time the universe proved us wrong and science moved forward by figuring out just how wrong we'd been. But those big moments had something we don't have now: clarity. The old anomalies were clear-cut. Neptune was real, and its gravity fixed the math. Relativity nailed Mercury's orbit. The cosmic microwave background showed up in every measurement. The data made it obvious. Here, why the old theory doesn't work, and here's the new one that does. 3IATLAS doesn't give us that. Instead, it gives us ambiguity. Data that almost makes sense if you bend the rules a bit, or might mean something strange if you don't. Observations that barely fit the usual comet playbook if you stretch the definitions, or break them completely if you don't. Nothing here is proof. It's just more evidence that we don't know as much as we'd like. Our models are incomplete, and the universe isn't lining up neatly. And that uncertainty isn't just academic, it matters. NASA and other space agencies need to predict the paths of near-Earth objects to figure out if anything's headed our way. If our predictions are off because we don't really understand how these things move, then the risks get harder to pin down. If we can't say for sure where a hazardous asteroid will be decades from now, we can't say for sure if it's safe. With 3IATLAS, there's no danger, so the stakes are lower, but the same problem applies. If we can't model this one object, how sure can we be about any of the others? This is where science shows both its strengths and its limits. The strength is honesty, sticking to the evidence, refusing to claim certainty when there isn't any, admitting when observations break the mold. No serious scientist working on 3IATLAS is saying it's definitely artificial or that it breaks the laws of physics. The papers are careful, measured up front about what we don't know. The feeling isn't triumph or certainty, it's genuine puzzlement. Science takes its time. To confirm a discovery, you need more than just one lucky measurement. You need teams repeating the work, reviewing it, double-checking everything. But sometimes, like with interstellar objects that sweep past Earth and never come back, the clock's ticking. You get a few months, if you're lucky, to look, to measure, to try to understand. When that window closes, that's it, the object's gone, and if you still have questions, tough luck. You can't chase it down for a do-over. The uncertainty stays, and everyone just has to move forward wanting answers that aren't coming. That's exactly what happened with Oumuamua. Long after it zipped out of sight, scientists kept arguing about what it even was. A weird comet, a chunk of planet, a frozen block of nitrogen from some Pluto-like world. Or was it something stranger? Nobody agreed because nobody could. The thing was gone. No more data, just scraps of observation and a lot of theories, none of which anyone could really prove or rule out, because the subject of the debate was already halfway across the solar system. The same pattern played out again in January 2026. Papers started rolling in, as they always do, each one carefully peer-reviewed, each title understated and precise. Orbital refinement of 3IATLAS using multi-station observations. Photometric analysis of interstellar comet 3IATLAS during Earth encounter. Non-gravitational acceleration parameters for 3IATLAS. Challenges and uncertainties. No hype, just facts. The abstracts played it safe. Here, the data. Here's what we did. Here's what we don't know. But if you dug into the results and you knew how to read between the lines, you found statements that mattered. Observed trajectory divergences remain poorly fit by standard non-gravitational acceleration models. Brightness variations show no correlation with expected solar heating patterns. The direction and magnitude of acceleration exhibit characteristics inconsistent with symmetric outgassing. In other words, we're stumped. Some teams tried tweaking the models. Maybe interstellar comets, after floating through deep space for millions of years, grow crusts that aren't like anything in our solar system. Maybe those crusts vaporize weirdly, giving the object a push without leaving the usual trails. Maybe the insides are full of hidden pockets of ice or gas, leaking in ways we can't see. All of these ideas stretched what we know, but they didn't break the rules of physics. If any of them turned out to be right, we'd learn something new about the wild variety of stuff drifting between stars. But they're still just guesses, and with 3IATLAS already too far and too dim, they'll probably stay that way. Other researchers tried a different angle. Some looked at the timing. Did the weirdness happen on a schedule, maybe tied to how the object spun or heated up? Some hunted for odd chemical fingerprints that might explain the activity. Others compared 3IATLAS with Oumuamua and Borisov, hopping to spot a pattern or a clue that linked them all together. And then there's the handful of folks who, while rarely saying it out loud in journals, started to wonder if maybe, just maybe, the explanation wasn't natural at all. Not because they were chasing UFO stories, but because they took the idea seriously. What if not every visitor from interstellar space is just a rock or a chunk of ice? What if, once in a while, something comes through that's actually built, not born? It's not about chasing headlines. It's about following the question astronomers have asked for years. If there's anyone else out there and they left behind artifacts, would we even realize what we were seeing? Enrico Fermi once asked a question that still hangs in the air. Where is everybody? If the galaxy's full of intelligent life, why haven't we seen any obvious signs? Some people think maybe we have. We just didn't know what we were looking at. Maybe an interstellar probe isn't a shiny flying saucer with blinking lights. Maybe it's a small, cold lump that looks just like an asteroid or a comet, unless you catch it doing something odd. That's the background for a bunch of off-the-record conversations about 3IATLAS. Scientists tossed around ideas, nothing official, mostly quiet speculation. If you were building a probe to travel between stars, they said, you wanted to steal energy from planets to keep going. You'd have it tweak its path whenever it passed something interesting, maybe to snap photos or settle in for a long look. And you wanted to keep a low profile, stay hidden from any primitive species that might be watching. Seen from that angle, 3IATLAS checked a lot of boxes. It changed course near Earth, check. It showed signs of propulsion, but nobody saw any jets, check. It didn't behave like anything people had seen before, check. Does that mean it's artificial? No. But is it worth thinking about? Some said yes. Here, where things get tricky, science needs hard proof. If you want to say something's artificial, you need unmistakable evidence. Radio signals, weird materials, geometric shapes, propulsion nobody can explain away. None of that turned up. The best photos, even the Hubbles, showed nothing but a fuzzy blur. No clear structure, no nucleus. People aimed radio telescopes at it and got silence. Spectroscopy picked up the usual comet stuff. Water, carbon dioxide, carbon monoxide, organics. Not finding evidence doesn't prove something isn't there, but it doesn't prove it is either. Science asks for extraordinary evidence when the claim is extraordinary, and 3IATLAS just didn't give it. Maybe it hinted. It definitely sparked curiosity, but nobody could point and say, there it is. So everyone just waited. Waited for a new interstellar visitor, hoping it would clear things up instead of making them more confusing. Waited for better telescopes and longer looks. Waited for time and technology to catch up, so when the next one comes, maybe we'll be ready. Meanwhile, 3IATLAS kept drifting farther away. By February 2026, it was already past Mars and growing fainter, almost out of reach for all but the biggest telescopes. A few months later, it would disappear beyond the asteroid belt, heading out to the deep cold and eventually out of the solar system for good. Soon, nobody would be able to track it. It would be gone, just another brief visitor, slipping back into the dark between the stars. But it stuck in people's minds. It left question marks in the data, unfinished conversations, and a sharp reminder that the universe is weirder and bigger than anything we're used to. Sometimes it feels like the cosmos just drops in to remind us how much we don't know. Space feels empty in 100 different ways. There's the obvious emptiness, the cold, the silence, the endless gaps between things. And then there's the emptiness of not knowing, of peering out from our little planet and realizing how much we can't see or understand. We watched 3IATLAS for a few months while it was close, but it had traveled, maybe for millions of years before it showed up, and it'll keep going long after it slips out of sight. What happened in all that time we missed? What's happening now, out where our instruments can't reach? We can run the numbers, predict the path, but that's all. We can't watch it any longer, can't know for sure if it keeps acting the same or if it changes in ways we never imagined. Because, in the end, we only glimpsed a tiny piece of its story. This is the real struggle of studying interstellar objects. Sure, they're messengers from other solar systems, but they also remind us just how limited our knowledge really is. Our view of the universe is so narrow. There's so much we miss simply because we can't look everywhere at once or chase these objects forever. Astronomers get used to this. They live with uncertainty. Their job is to stare at ancient light and guess what's happening right now from photons that took years, centuries, or even millions of years to reach us. They build models out of scraps. They make predictions with the full awareness that they might be wrong. They know the universe doesn't hand out answers whenever we want them. Some questions just stay open. But 3IATLAS pushed that tolerance in a different way. This wasn't your average incomplete data set or a slightly off model. The object hovered right on the edge. Maybe it's explainable, maybe it's something we've never seen before. It danced between the limits of known physics and the possibility of something entirely new. You couldn't honestly say, oh, that's natural, but you also couldn't claim, nope, that has to be artificial. You're left hanging, knowing only that something weird happened and you don't really get it. People hate being left in limbo like that. We want answers. We want to know, is this just something we don't understand yet, or is it truly out of the ordinary? We crave neat categories, comet or probe, natural or artificial, solved or mysterious. But the universe rarely hands out those labels, especially not on a human timeline. Sometimes all you get is a burst of data, a bunch of new questions, and then the object is gone. No more chances. That's exactly what happened with Oumuamua. Years after it sped off, scientists still argue about what it was: a weird comet, a chunk of a planet, a nitrogen iceberg, or something stranger. The debate drags on because the object is gone. No more data, just competing theories, none of them fully provable without the thing itself. 3IATLAS could easily become another Oumuamua, a mystery that slips into scientific folklore. People will cite it in papers, debate it at conferences, use it to argue about how many interstellar objects are out there, but never quite solve it. The one thing that matters, the object itself, is out of reach. There's a kind of sadness to that. The universe gives us these brief glimpses. A visitor from deep space swings by, and we scramble to learn whatever we can before it disappears. We build new telescopes, invent new tools, team up across continents, analyze every scrap of data, and write it all down. Then it's over. The visitor is gone. The chance is lost. All we have left are our measurements, our questions, and the sinking feeling that we'll probably never get another look. But honestly, there's something pretty amazing about the encounter itself. For a little while, we got to watch matter from another star system up close. We measured its makeup, tracked how it moved, watched its behavior. We learned that interstellar comets can be loaded with carbon dioxide, that they can flicker in brightness in ways we don't expect, that their paths can drift from what basic gravity predicts, and we still don't know exactly why. These things matter. They're puzzle pieces, and it'll take decades, maybe centuries, to see the full picture. Every time an interstellar object crosses our path, we add to our understanding of what's out there, even if each one leaves us with more questions than answers. And honestly, just looking matters. When a telescope operator in Hawaii aims a giant mirror at a faint dot, when an engineer in California codes up the tracking that keeps that dot in view for hours, when a scientist in Massachusetts sifts through photons that crossed millions of kilometers to hit a sensor, there's something old and important happening. It's the drive to understand, and that's as human as it gets. That drive to understand the universe isn't in any rush. It doesn't insist on answers right now, not this year, not even this generation. Honestly, the hunt for meaning stretches out over centuries, way beyond a single human lifetime. Aristotle asked about the cosmos thousands of years ago, and those questions still matter. Tycho Brahe watched the sky in the 1500s, and his work helped Kepler and Newton figure out gravity and planetary orbits decades later. And the stuff we're learning about 3IATLAS today, we might not really get it until someone in the future, someone who hasn't even been born yet, looks back, puts the pieces together, and finds meaning we can't see right now. You don't hear much about this slow, generational side of science. Most stories highlight those big eureka moments or focus on lone geniuses making breakthroughs. But the truth is, science moves forward one step at a time, with every generation picking up where the last one left off. Each group tries its best, then hands off its questions, new data, and sharper tools to the next set of thinkers. It's a team effort, and it never really ends. No single person or era figures out everything. There's just too much out there, too many mysteries for any one mind or moment to handle. So when astronomers studied 3IATLAS and didn't answer every question, they didn't fail. They joined the chain. They gathered data that others will use. They built models that someone else will tweak. They raised questions that'll drive tomorrow's discoveries. Not having every answer doesn't make their work less valuable. It just puts it in context. It's one chapter in a story that's still being written. And maybe that's how it should be. Maybe the point isn't always to tie everything up neatly, but to face the unknown with curiosity and honesty. Maybe what matters most about 3IATLAS isn't the answers it gave, but the new questions it forced us to ask. What counts as truly weird? When does weird cross over into anomaly? How do we know if we're missing something, or if something genuinely new is happening? What does it take for us to take bizarre possibilities seriously? And how do we keep our skepticism sharp without shutting ourselves off from surprises? Questions like these will outlast 3IATLAS by a long shot. They'll be waiting when the next interstellar visitor swings by, and the one after that. They'll shape how we plan observations, which instruments we build, what kind of data we pay attention to. They'll guide arguments about where to spend our money and time, how to juggle competing research goals, and how to talk about what we find, without either hyping up vague results or downplaying real discoveries. Now, when it comes to sharing science with the public, things get tricky, especially with something as strange as 3IATLAS. On one side, people deserve to know what scientists are learning. Taxpayers fund a lot of this work. The knowledge belongs to everyone, not just the experts. So there's a real need for openness, for sharing both the wins and the uncertainties. But talking about uncertainty is hard. People want clear answers. Is 3IATLAS a comet or not? Did it change direction or didn't it? Telling folks, well, it's probably a comet, but it acts a little odd and doesn't quite fit our models, just doesn't satisfy anyone. It sounds slippery, even though it's the most honest thing you can say. This gap opens the door for hype and wild stories. The media loves a headline that says, "Scientists baffled by mystery object, way more than object's behavior needs more study." But the first headline invites all sorts of speculation and wild claims you just don't get with the second. Pretty soon, the public sees anomaly and thinks aliens, or hears uncertainty and assumes there's a cover-up. Careful, honest scientific language gets twisted into something it's not. The researchers working on 3IATLAS knew all this. They chose their words carefully in their papers, aware that all kinds of people, some experts, some not, some with their own agendas, would be reading. When talking to reporters, they stuck to what they could actually back up. Sometimes they kept certain ideas to themselves, not because they were hiding anything, but because tossing out wild guesses without evidence would just confuse people and feed the rumor mill. So 3IATLAS really did its job as a visitor, even though it left us with more questions than answers. It didn't hand us any neat solutions. Instead, it showed us exactly where our understanding falls short, where our models start to wobble, where we need to dig deeper. That's a little unsettling, sure, but honestly, that's how science moves forward. The weird stuff, the things that don't quite fit, they're usually the most important clues we get. Part 5, the open question. It's late February 2026. As I write this, 3IATLAS has already slipped past Mars's orbit, speeding away from the Sun at about 30 kilometers per second. Give it a few more months and it'll cross the asteroid belt. A few years down the line, it'll pass Jupiter. Wait a few decades and it'll shoot past Neptune, back into the space between stars, the place it started from, heading out into the dark. We won't see that happen. By summer, even our biggest telescopes won't be able to spot it. It'll blink out of view, invisible, untrackable, gone as far as our instruments are concerned. But it won't stop existing. 3IATLAS will keep moving, following its own path, shaped by its momentum and whatever forces nudge it along. That's the weird thing about space. Just because we stop seeing something doesn't mean it's gone. These objects keep traveling through the cosmos, doing their thing, whether we're watching or not. And we're left to wonder, is it still acting the way it did before? Has something changed? Is it out there right now doing something that would finally answer our questions if only we could see it? There's a psychological side to all this. Humans are wired to find patterns. It's a survival thing. We learn to pick out the sound of a predator hiding in the grass, to spot faces in the shadows. This knack for pattern spotting helps us in daily life, but in science it can trip us up. When the data gets fuzzy, our brains rush to fill in the gaps with stories, explanations, anything that makes the chaos look like order. Sometimes those patterns are real. Other times it's just us projecting meaning onto randomness, pareidolia, but on a cosmic scale. Telling the difference takes more than intuition. You need stats, independent checks, alternative ideas tested and retested. Science gives us these tools. They don't erase our urge to see patterns, but they do keep it in check, forcing us to lean on evidence instead of running wild with guesses. With 3IATLAS, this tug-of-war between instinct and skepticism played out in real time. Some researchers looked at its odd trajectory near Earth and saw a pattern. The timing felt too perfect. The direction lined up exactly with a gravitational assist, and the effect seemed too big to explain with something as simple as outgassing. To them, it hinted at intent, or at least a process we'd never seen before. Others saw the same data and shrugged. All they saw was noise or ambiguity. They pointed out that with enough observations, some will always look weird just by chance. Besides, we barely understand outgassing in interstellar comets. Our sample size is tiny. Unusual isn't the same as impossible. And leaping from "we can't explain this" to "it must be artificial" has led science off track more times than you'd think. Both sides have a point. Both are reasonable ways to deal with the unknown, and both will shape how we talk about discoveries like this in the future. The real challenge is finding the right balance, staying open to surprises without throwing evidence out the window, keeping our standards sharp but not so rigid that we miss something real. Go too far in either direction and you get problems. Believe every anomaly and you end up chasing fantasies. Doubt everything and real discoveries slip through your fingers. Astronomy's history is full of both mistakes. Back in the late 1800s, astronomers thought they saw channels on Mars. They turned those lines into canals and jumped to the idea of Martian engineers. Later, better telescopes revealed nothing but optical illusions, a classic case of pattern seeking gone too far. On the flip side, when pulsars first popped up in the 1960s, the signals were so steady that astronomers half-jokingly labeled them LGM-1, for little green men. But instead of running with the wild idea, they dug deeper, kept looking for natural explanations, and finally figured out it was just neutron stars spinning. That's skepticism working the way it should, holding out for real evidence before making the leap. The thing about 3IATLAS is, we only got one shot. It swept through our solar system, we scrambled to collect as much data as we could, and then it was gone. That's it, no second chances, no repeats. What we're left with is a patchwork of observations that can point in a bunch of different directions. It's nothing like studying pulsars, where you can keep coming back year after year, watching them pulse away, learning more as your tools get better. With 3IATLAS, that door slammed shut fast. Some of the questions it raised, we might never get answers, at least not from that object. For scientists used to running experiments, tweaking variables, repeating tests, nailing down cause and effect, this sort of thing is maddening. Astronomy doesn't care about your desire for control. Especially when it comes to fleeting events like this one, you just take what the universe throws at you when it throws it, using whatever gear you have on hand. Miss your chance and all you get is regret. But there's something kind of beautiful about that too. You have to be sharp. You squeeze every bit of meaning from whatever scraps you manage to collect. You learn to live with uncertainty, to accept that sometimes probabilities are all you've got. It's humbling. You get used to asking, what do we really know? And being okay when the answer is, not much. The last time anyone got a decent look at 3IATLAS was in early February, and even then it took the Hubble Space Telescope to pull it off. Hubble's great, but even it struggled, just a faint smudge, barely above the background noise inching across the stars. The measurements were shaky. The brightness estimates, big error bars, not much to hold onto. Still, each new data point helped a little, nudged the trajectory calculations in the right direction. But it was obvious we were running out of time, and then we ran out. By mid-February, not even Hubble could spot it. The last position was logged, the final image saved. Just like that, 3IATLAS went from something we could chase to something we could only remember and keep wondering about. Scientists will keep digging through the data, publishing papers for a while yet. But these are just new spins on old observations, not fresh discoveries. The real action is over, sooner or later. 3IATLAS will just be a footnote, a weird case astronomers bring up when talking about interstellar visitors, a reference point for next time. But the questions it left behind, those aren't going anywhere. Did the weird change in its path as it passed Earth come from a perfectly timed gravitational slingshot, or was it just a lucky burst of gas that nudged it at the right moment? Was the flickering in its brightness a sign of some hidden structure or something stranger, maybe a process we haven't even imagined yet? And what about those jets we didn't see? Did we just miss them, or was something else at work, something we've never encountered? Right now, nobody knows. Maybe someday we'll figure it out, maybe not. But 3IATLAS forced astronomers to rethink what these interstellar visitors might be. There's more caution now. A sense that not every object zipping through space is just a dumb rock on autopilot. Some are going to surprise us. And sure, there's always that wild possibility. Maybe, just maybe, something artificial is out there. It's a long shot, the least likely scenario, but you can't rule it out until you've ruled out everything else. With just a smudge and a handful of data, we can't do that. Maybe the next interstellar object will make things clearer. It might behave exactly like we expect, follow all the rules, and make 3IATLAS look like a one-off. If that happens, we'll tweak our models, chalk this up as an oddball, and keep going. But until then, the mystery lingers. Maybe the next visitor acts even stranger. Maybe it shows off obvious signs of maneuvering, or sports some structure we can actually see in the images, or blasts out radio waves we just can't chalk up to nature. If that happens, everything changes. Suddenly the debate isn't academic anymore, it's urgent. What are we looking at? Who or what sent it? Does it want something? Or is want even the right word? But honestly, the most likely scenario is the next visitor shows up with surprises we didn't even think to expect. It'll throw us fresh questions, leave us with new mysteries. Every interstellar object seems to catch us off guard. Oumuamua looked nothing like what people had imagined. Borisov seemed normal, at least until scientists took a closer look and found weird chemical traces. 3IATLAS seemed ordinary until it didn't. That's the trend. No real trend at all. Or if you squint, the trend is just variety. The galaxy churns out all kinds of little travelers, and they never quite act the same. Some are icy, others rocky. Some are untouched, others altered by time or heat. Some just drift along, others get weirdly active. Some play by the rules, some make up their own. And that's exactly why interstellar objects are so fascinating. Each one gives us clues about far-off solar systems, about how planets and smaller bodies form, about the mix of stuff floating around the galaxy. But it also means every new visitor could be a fresh anomaly, and it gets harder to tell what's just odd and what's truly unexplainable as more of them show up. We're getting better at catching these visitors. The Vera C. Rubin Observatory in Chile is nearly ready to scan the whole southern sky every few nights, building up a live map of anything that moves. Its huge mirror and super-sensitive detectors will spot things fainter and farther away than we've ever managed before. Other observatories are in the works for the northern sky, so coverage just keeps expanding. Because of these upgrades, we'll spot interstellar objects more often and sooner. Instead of noticing them only when they're already zooming through the inner solar system, we'll catch some out near Jupiter or Saturn, giving us months or even years to watch instead of just a few frantic weeks. That extra time means we can actually figure out what we're looking at, nail down whether something's truly weird or just misunderstood. Space telescopes help too. The Nancy Grace Roman Space Telescope, set to launch soon, will scan the skies in infrared, filling in the gaps the ground-based observatories leave. The James Webb Space Telescope keeps churning out data, letting us dissect the makeup of cometary clouds in ways we couldn't dream of before. Down the line, we might even send special spacecraft, interstellar interceptors, ready to launch as soon as a visitor shows up, racing out to meet it while it's still close enough to study. All this new tech matters because it changes the questions we can actually answer. With better data, we can finally test ideas that have just been speculation until now. We can figure out if strange orbits like 3IATLASes are rare flukes or actually common. We can measure things precisely enough to sort out which explanation really fits. We can build up enough examples to see real patterns instead of just random coincidences. But no amount of fancy instruments will clear up every mystery. Some questions are just tough, no matter how good the gear gets. If we want to know if something's artificial, we have to spot unmistakable techno-signatures, and even if it's there, we might not see it. If someone built a probe to stay hidden, coasting quietly and using almost no active systems, it could look just like a natural object, no matter how hard we stare. Here's the kind of scenario that keeps some astronomers up at night. What if we're getting regular visits from other civilizations, but their artifacts slip through our solar system all the time, built to hide, or made to blend in so well with natural objects that we just don't notice them? In that world, every weird interstellar object could be a probe. Any unexplained movement looks suspicious, like someone steering it. Suddenly, we're stuck wondering if we're alone or if there are watchers everywhere, hidden in plain sight. Sure, it's a wild idea. There's no solid evidence for it, and honestly, it probably isn't happening. Still, it's not completely off the table, and that tiny chance shapes the way we treat cosmic oddities. If we shrug off every strange blip as something natural and move on too quickly, we risk missing the one real sign that changes everything, proof that we're not alone. That's a huge deal. Of course, this leads to a real headache. Chasing down every anomaly eats up resources, telescope time, researchers' attention money. There's never enough to go around. Too much focus on long shots means less progress on the bread and butter science we know works. But if we ignore the weird stuff, we guarantee we'll never spot the genuinely strange when it shows up. Different groups tackle this in their own ways. Some, like Harvard's Galileo project, make the search for possible techno-signatures a priority. They know most trails will go cold but think the payoff, finding something artificial, is worth the risk. Others stick to the view that regular astronomy will turn up anything truly odd, so there's no need for special searches. Weird objects will pop up in the usual data and then get a closer look if they really stand out. Both strategies matter. Focused searches make sure we don't overlook the unusual. Standard research gives us a solid baseline, so we even know what counts as an anomaly. Together, they make the science stronger than either approach alone. Meanwhile, the objects themselves just keep moving past us. 3IATLAS fades into darkness. Oumuamua, spotted in 2017, is now way beyond Pluto and heading back out to interstellar space. 2I/Borisov came and went, returning to wherever it started. Each left behind data, arguments, and questions that haven't faded, even though the objects themselves are gone. There will be more. Some will spot, some will slip by unnoticed. A few will get months of attention, others just a passing glimpse before they disappear. Every one of them brings clues about where it came from, what it's made of, and what it's been through. Some will back up our theories, some will break them, some just leave us scratching our heads. The universe doesn't owe us easy answers. It wasn't made for us to understand. The fact that we can figure anything out about this place, that math we cooked up on this planet can describe things happening light years away, is kind of amazing when you think about it. When we hit something that doesn't fit, it's not the universe's fault for being confusing. It's just a sign that our models are temporary, unfinished, always up for revision. 3IATLAS was that kind of reminder. Not because it proved anything wild, but because it refused to fit neatly into a box. It pushed the limits of what we can explain without quite breaking them. It left us with more questions than answers, and that's the real job of astronomy, to show us where our knowledge ends and where our curiosity has to take over. Discovery lives right at the edge between what we know and what we don't. That's where new theories pop up, where everything shifts, where we push the boundaries of what we understand about the universe. You won't find comfort there. You won't find tidy answers, just the odd stuff, the things that don't fit, the mysteries that refuse to go quietly. So maybe instead of asking, what was 3IATLAS, we should be asking, what did 3IATLAS teach us? And honestly, the lesson isn't really about the object itself. It's about how we deal with uncertainty, with the unknown, with a universe so big and weird we can barely wrap our heads around it. 3IATLAS showed us that interstellar space throws things at us that are way stranger than what we're used to in our own solar system. It reminded us that comets from other stars don't have to play by our rules. Predicting their paths isn't simple. The usual methods start to wobble when we're dealing with stuff we don't fully get. The galaxy still has surprises up its sleeve. Our models aren't perfect, and admitting the limits of what we know isn't a sign of weakness, it's wisdom. Maybe the most important thing it taught us: pay attention. Watch the sky like it's trying to tell you something. Gather data like it matters because it does. Analyze it honestly. Be willing to change your mind. Stay open to being surprised. More interstellar visitors are coming, and with everyone we'll pile up more data, more weirdness, more patterns, more chances to figure out what's really out there. That big picture might turn out to be pretty reassuring. Maybe the galaxy is just full of natural objects, comets and asteroids drifting through space, doing what physics tells them to do. Maybe the odd stuff is just natural variety we haven't seen before. If so, that's great. It means our science works. The universe can be understood, at least mostly, but maybe not. Maybe we'll find things that don't fit any natural category, behaviors that don't make sense, patterns that hint at something intentional or just totally new. That would change everything. It would mean we've been missing something big, that the universe is far stranger, and that we might not be alone after all. Either way, it matters. Either way, discovery changes us. But we'll only know if we keep looking carefully every time the universe tosses something new into our corner of the sky. The sky isn't quick to spill its secrets, but it does eventually if you watch closely enough and let yourself be surprised. We're on the edge of a new era soon. Spotting interstellar objects will be almost routine. New telescopes, sharper instruments, better algorithms, they'll all help us find more of these visitors. In a decade, we might spot 1 or 2 a year. In a few decades, maybe dozens. Each one gives us a fresh chance to study matter from somewhere else in the galaxy. And every time we'll face the same questions. Is this just another rock? Or is it something different? Is there even a chance it's the first real sign of non-human intelligence? That question, honestly, is why 3IATLAS still matters. Not because it proved anything artificial, because it didn't, but because it showed us how unprepared we really are. We can't reliably tell the difference between a weird natural object and something built by someone or something else. Our tools aren't sharp enough, our models aren't broad enough, our sense of what's possible is still too narrow. If some kind of interstellar probe slipped through the solar system, using gravity to boost its speed, keeping a low profile so we wouldn't notice, would we even recognize it? What would it take to convince us? And are we even looking for the right clues? These aren't just questions for late-night debates. They shape how we plan our observations, what kinds of data we chase, what weirdness we take seriously. If we're not thinking this way before the next strange visitor shows up, we'll miss our shot to catch something amazing, while it's still right there, waiting to be seen. Some places are actually taking all this seriously. Over at Harvard, Avi Loeb and the Galileo Project are putting real effort into hunting for signs of alien technology, things like weird interstellar objects that don't quite fit the usual mold. They're not just waiting around, either. The team is coming up with ways to react fast when something odd shows up, figuring out how to grab the right data, and trying to set ground rules for sorting out what's natural and what's maybe not. They're also thinking hard about how to talk about stuff that isn't clear-cut without jumping to wild conclusions. Of course, not everyone is on board with this approach. Some scientists are pretty skeptical. They say chasing after artificial explanations too soon just isn't good science. It could even make the whole field look bad. For them, it's simple. Rule out every natural explanation first, and only then, if nothing else fits, start thinking about the weird stuff. That's the classic scientific playbook: slow, steady, and careful, always guarding the reputation of the field. Honestly, both sides have a point. Both are going to shape what happens next. Most of these mysterious visitors are probably just rocks or ice from somewhere else, nothing more. But it makes sense to keep an open mind because the risk of missing something huge is just too high. If we ever do stumble across a real artifact from another civilization, recognizing it would be huge. Missing it just because we assumed everything's always natural, that would sting. But jumping the gun and calling something alien tech without solid proof, that hurts science too, and it makes it even harder for anyone to believe us if real evidence shows up later. That's the balancing act astronomers face with objects like 3IATLAS. They have to stay open to the wild possibilities, but still keep their skepticism. They have to notice when something feels off, but not rush to a headline. And when things are uncertain, they have to say so, without downplaying real mysteries or hyping up what might turn out to be nothing. None of this is easy. In fact, it's probably impossible to get just right. But it's the job now, especially as our telescopes get sharper and we start spotting more of these passing visitors. So we wait. We wait for the next strange object to swing by. We wait for better tools, longer looks, and the lucky break that finally gives us answers. We wait, knowing the universe doesn't care about our schedules. Some answers might take decades. Some might never come at all. But while we're waiting, it's worth thinking about what 3IATLAS taught us. Not final answers, but hints at how messy and surprising the galaxy can be. Not proof of something extraordinary, but a nudge that maybe our models don't catch everything. Not closure, but a reminder to keep our eyes open, to question what we think we know, and not to hold too tightly to certainty. That object that zipped past Earth in December 2025 didn't slow down the way we expected. Was it doing something purposeful? Or just following some natural rule we haven't figured out yet? We still don't know, but it changed the conversation. It forced us to look harder, to wonder about what we're really seeing, and to remember that the universe still has plenty of surprises in store. And maybe the biggest question it left us is this: what if we're not seeing things the right way? What if our ideas about these interstellar visitors are just too limited? What if the universe has been trying to get our attention all along, and we've just been missing the message because we don't know how to listen? Some questions just don't go away. 3IATLAS is long gone, but those questions are still waiting out there, waiting for the next visitor and the one after that. The sky isn't in any hurry to spill its secrets, but if you're patient, if you pay attention, and if you let yourself be surprised, sometimes it does. Now, 3IATLAS has slipped out beyond our reach. We can't study it anymore. But it left something behind, questions that linger and a certain humility that settles in when you realize how small and unknowing we really are. We live in a universe that's bigger and weirder than our little world can show us. Sometimes the most valuable discoveries aren't answers at all. They're reminders of how much we still don't know. The visitor came and went. We grabbed as much data as we could. Now the work goes on. And somewhere out there, moving fast and silent into the deep dark, an object carries mysteries we can't chase and questions we can't answer. That's not science failing. That's just the cosmos being the cosmos. Living with uncertainty, learning to value the questions, not just chase after quick answers. That's maybe the best thing 3IATLAS had to teach us. The universe doesn't owe us explanations. What it gives us, if we're lucky, is wonder. And a lot of the time, wonder is enough. Across the globe, in cold observatories and warm labs, people stay up late, staring at data, running numbers, trying to trace the impossible paths of objects through space. We keep watching, we have to. Curiosity is in our bones. The questions matter even when the answers slip through our fingers. Somewhere out there, another visitor is already on its way, threading through that vast darkness toward our sun. When it arrives, we'll be ready, smarter, better equipped, carrying the lessons of 3IATLAS and everything else we've managed to learn. We'll ask sharper questions. We'll collect better data. Maybe we'll get a little closer to understanding, but that sense of wonder, we're never letting go of that. The universe is too big, too strange, too far beyond what we can ever fully wrap our heads around. That's not a dead end, it's an invitation to keep looking, to keep asking, to keep letting ourselves be amazed. The stars don't care if we're watching, but we watch anyway. And in that watching, we change. We connect just a little to the vastness we'll never fully grasp but can't stop reaching for. 3IATLAS is gone, but the mystery is. The sky still has things to teach for anyone patient enough to listen.